Balance problems consider the location of the fulcrum as the basis for formulation. Understand that rotation can happen when a force is applied to one side of a lever or a beam. Learn how to solve balance problems here. Welcome to Mathematics of Engineering. Let's dig a deeper understanding of the applications of linear equations in balance problems with the first example. A and B together weigh 242 pounds. They balance when A is seated 5 feet from the fulcrum on one side of a lever and B is seated 6 feet from the fulcrum on the other side. Find the weight of each. From the first statement, we can identify the total weight of A and B as 242 and consider this as equation 1. The second equation will integrate rotation in the procedure. Rotation is computed as force multiplied by the distance. However, to keep the lever balanced, the clockwise rotation would be equal to the counterclockwise rotation. Or simply said, the rotation is taken as 0. From our example, we can get distance of 5 feet multiplied by the weight of A will be equal to the weight of B multiplied by his distance from the fulcrum taken as 6 feet. By extracting B, we get B is equal to 5/6 of A. This is the second equation. By substituting equation 2 into equation 1, we would get A plus 5/6 of A is equal to 242. So A can be simply computed as 132 pounds. And again, replace A with 132 pounds in equation 2, making it B is equal to 5/6 of 132. Then B is computed as 110 pounds. Let's work on the second example. A uniform beam 15 feet long weighs 3 pounds per linear foot. At what point should it be supported by a fulcrum if a weight of 25 pounds on one end is balanced by a weight of 65 pounds on the other end? The unit weight multiplied by its length is taken as the total weight of the beam. In the example, 15 feet of 3 pounds per foot is equal to 45 pounds. The total weight is always applied to the center of the beam. Take note that it is the center of gravity. If we denote x, the distance of the fulcrum as referred to the left end, the remaining distance is taken as 15 less x. Moreover, the placement of the weight will be at 7.5 feet, leaving x minus 7.5 for the fulcrum. For the beam to be balanced, the rotation is taken as 0. That is, the clockwise rotation is equal to the counterclockwise rotation. So by plugging the values, the equation becomes 25x plus 45 times x minus 7.5 is equal to 65 times 15 minus x. And by expanding, we get 25x plus 45x less 337.5 is equal to 975 minus 65x. And arranging the terms, we would reach 135x is equal to 1312.5, whereby dividing both sides by 135, x, or the distance of the fulcrum from the left side, is computed as 9.72 feet. The third problem. John, Peter, and Jane weigh 80, 60, and 50 pounds respectively. John sits 3 feet, Peter sits 5 feet, and Jane sits 6 feet from the fulcrum on the same side. How far must their 200-pound father sit from the fulcrum in order to balance them? After translating the statements properly, we are going to work with rotation of beam upon considering the characters as forces, with the required as the location of the father from the fulcrum. Again, for balanced beam, the rotation will be taken as 0. That is, the counterclockwise rotation is equal to the clockwise rotation. So by plugging the values, we get 80 times 3 plus 60 times 5 plus 50 times 6 is equal to 200x. We can simplify the equation as 840 is equal to 200x, and by dividing both sides by 200, x is taken as 4.20 feet. That is the distance the father should sit from the fulcrum.